record this thing. So today, everybody, we're going to start studying algebraic limits.
Is that piece of paper that you have there the notes sheet?
It is. It's the one for algebraic limits, which should be in there.
All right.
And
I'm going to need to print that out.
you can, or you could write it on scratch paper, and it's fine. However works best for you, Gene. So anyway, this is what we're going to look at. So there's a few things to look for. So just like remember the 12 things that we looked at before at the beginning of last year, I wanted you to know what square roots look like. I wanted you to know what parabolas look like, absolute values, etc. There's certain things that I would like you to know how to deal with in terms of finding the limit of an algebraic sense. Now, yesterday we did limits at infinity, right? Today, we're not always going to be doing infinity. We're going to be doing it at an independent spot. So like, for example, this one right here, we're literally going to say cosecant. What happens is I get really, really close to the cosecant of 5 pi over 3. Well, I told you, I just poked my sister. If they say don't do it, I'm like, well, what happened? Boom, I got punched. Okay, I now know what happens. But that's what we're going to do. We're going to just go ahead and say, screw it. It says get really close to 5 pi over 3, so I just say, well, fine, I'm going to do that. What happens if I literally plug in 5 pi over 3? Well, a couple things happen here. Yes, we do need to remember some trig. What quadrant is 5 pi over 3 in? 5 pi over 3 is almost 6 pi over 3, which would be the entire way around, so it's actually down in quadrant 4. And so since it's down in quadrant 4, I know that the sign where the cosecant comes from is negative. And then I have to remember my unit circle. What is the sign of any kind of pi over 3? It is root 3 over 2, so that would be 2 over root 3. Now, what I can tell you is eventually in calculus, I would just say write that down, smile, and move on. Last year, I made you fix it, didn't I? In calculus, we usually don't bother to fix it because we've got more significant things to deal with. But we could write negative 2 roots of 3 over 3, because if it's a simple problem, it's probably worth the time. How about this guy right here? What happens if I get really close to negative 4 from the negative side? What does it get really close to? Well, again, what did I say? Just plug it in. What happens? You get 2. Fine. Nothing blew up, right? So what we do in those problems is you literally just plug it in and hope for the best. See what happens. So direct substitution is actually the first thing you do. It's like in factoring how the first thing you always do is GCF, right? In limits, the first thing you do is just plug it in and hope for the best. And if you get a good answer, fantastic. But if you ever get something that is this form right here that looks like something that is not 0 over something that is 0. Now, you can see this is actually rigged up to do this. Why are we saying not 0 over 0? Because we studied something last year, remember? What happened if it was 0 over 0? What was the 0 over 0?
A hole.
That was the hole. Very good. That was what we called a removable discontinuity. And if there's a hole, would the limit exist if there is a hole? Yeah. But look what it says. It says the bottom is 0, but the top isn't 0. Do you follow? So is this a hole? No. So that either means that that limit is going to be infinity, because when you divide by 0, you get a vertical asymptote, right? As long as it's not a hole. But, so what is going to happen if I come at it from the high side? Because technically it's D and E, but we really would rather say more specifically what kind. Is it positive or negative infinity? Why? Well, because if I come from the high side of 1, what's the top? It's something very, very, very close to the number 2, isn't it? Now watch my notation. This is kind of bad notation, but you're going to buy it anyway. If I'm a little bit above 1, don't I get really, really close to 0? But in kind of a positive way, am I getting really close to 0, but from the high side of 0? So I've got a positive over a positive, which would be, of course, positive. And that's kind of the way I would like you to actually note that.
Mr. Benner?
Yes.
Where did you get 2 from?
Oh, because if I got really close to the number 1 and I cubed it, I'd still get something very close to 1. Plus 1, and I get something really, it's not identically 2, but very, very close to
Oh,
2.
okay. Okay, thank you.
Now, you may not remember what the sign looks like, but that's the deal, right? That's what a sine wave looked like from 0 to 2 pi, right? So this says what happens as I approach pi. So let's talk about it. What happens is I get really close to pi, but from the high side of pi. Well, the top is getting very close to pi, isn't it? Because it's just x. And what's the bottom? The bottom is getting very, very close to 0, but keep in mind I'm approaching from the high side, from above pi. So it is getting close to 0, but where is it the entire time until it reaches 0? It's just a smidgen underneath, is it not? It will always be negative until I actually reach pi. So what would you guys say that answer should be?
Negative infinity.
It's going to be negative infinity. Okay, as you go to infinity, we talked about these. Again, this is algebraic limits. This actually goes with what we did yesterday. What happens here if you approach infinity? We're just trying to be thorough. Negative 5 over 4, that one should be an easy one. And how about the natural log of the absolute value of x? What's that? Positive infinity. This is the slowest. Corpy talks about this one. It's really, really bad. It's like the slowest race to infinity you could imagine, right? We talked about that. How long, you know, if it was base 10, it's easier to understand. How long did it take to get to like 9? It took 1 billion steps to the right to get to a height of 9. Is it making it to infinity? It's the slowest race to infinity that you can possibly imagine. It's worse than watching paint dry.
It's heading toward negative infinity. Does that change anything?
Well, no, the cool thing is there was an absolute value on that, wasn't there?
Which
So
means
if
it's
you
like,
recall, if I replaced, let me ask you guys a question. What would happen in this story if I replaced x with negative x? Would it change the natural log of that absolute value? So guys, that actually means it's an even function. This graph actually looks like this on the right side. What does it look like on the left side?
the exact same.
The exact same thing with a mirror image because it was an even function. So both sides are a really terrible race to watch to infinity. I know some of you probably hate watching golf, but this would make golf look really, really rivetingly exciting. Now, I'm not doing that. I actually like watching. Do you like playing golf? See, Curtis likes why does Curtis like watching golf? Is because he plays it. He can appreciate what those people are doing. If you've never played golf, it's a terrible sport to watch. But if you have played golf, you can be like, wow, that's a pretty amazing shot. I wish I could do that. That's pretty fun.
Hit ball with stick and be quiet about it.
Hold your stick and be quiet about it. Is that what you said?
I said hit the ball with the stick and be quiet about it.
Oh, well, yeah, it is a challenge. It is the most humbling sport, I think, that can exist because you can go from a hero to a loser in 2 seconds. So anyway, okay, you guys okay with piecewise? Talked about that a little bit. So keep in mind if you say the limit is 2. So one of those things is the nomenclature of calculus is very picky. Do you notice what does exist in this problem that makes it very different than both of the ones in example 2A and B?
It doesn't have a denotion
It doesn't
of
have
which
a
side is coming
qualifier,
from.
so it's saying both sides. So what I'm saying is the answer the same from both sides? So in order for me to answer this question, I must consider that answer, and I must consider that answer, and what must be true? They have to be identical, the road in and the road out. Now, does it have to be the same? The question that I have, does it have to be the same as f2 itself?
No.
No. If all 3 were the same, that was the definition of continuous. That's a little bit different. You don't have to be continuous to have a limit. So let's look at the underside. Be the top equation. What's the underside of 2? This would get really close to 4. Minus 3 is 1. And from the high side, now keep in mind, does this say I can use 2? No, but we already said it. Just screw it. Just plug it in anyway. If you've got really close to 2, this is going to get really close to 1 plus 1, which is 2. So what do you want to say about the limit?
Does not exist.
Oh, it does not exist at all. There is no way, because those two values must in fact be true. Now, this problem right here is kind of weird because they gave us the sign of x like this. And do you notice what I did? I put an open dot at pi because they said it didn't exist there, correct? But they said at the number pi, go ahead and put a dot right up here at 1. Now, this is not critical that you actually graph it, but sometimes it's helpful to have that visual imagery, right? What do you guys think? Does the limit exist as I get close to pi? From the high side, what does it get close to? 0. From the low side, does it also get close to 0? So what I'm going to say is the limit as x approaches pi from the high side is the same as the limit as x approaches pi from the low side, which then means that is the limit as x approaches pi, which is in fact. Now that's a lot of work to write all that stuff down, but that's really what I'm trying to say. I'm trying to communicate to everybody else that I actually thought about it. Did I look at the high and the low and make sure they were in fact the same? So far, does this seem to be pretty doable? I think it's mainly a repeat of things that we have done before, but things are going to start getting a little bit weirder. Okay, squeeze theorem. Again, we've already seen this. This is a fairly typical thing. I've actually seen this on AP tests before, but if you want to find out that this is true, in an inequality, can you guys use an operator and add 4 to this one, and this one? Could you do that?
Mm-hmm.
Could you multiply all 3 of them by 2 or something like that? You could do all those. Well, the kind of the cool thing about that is if you are asking that, you can do the same thing with limits, and you can distribute a limit through a problem. So notice I'm just going to rewrite the question as it was stated with the addition of one little piece. And I know that for some of you guys that are not real formality people, this is a little bit irritating to take the time to write all this down, but that's actually what the math says you're supposed to do. In the same way that you would square both sides or you would take a square root of both sides, you can do the same thing. You can operate on the entire thing with a limit. Now we got to think about this. What happens is I get really, really close to the number 1 over here. That would be e minus 1. Now, I don't know anything about j of x. I just happen to know who j is always smaller than, and I also know who j is always bigger than, but will that tell me anything about j itself? So what happens is I get really close to 1 here. You know what? I was a little careless about that, but it's okay. There's this, it's the natural log of x, and then the x squared is sitting on the outside because there's no parentheses, so be a little bit careful. What is the natural log of 1? Do you know? Remember we said, what's the exponent? E to what power is 1? 0. The natural log of 1 should be 0. And if I plug in that, I get 1. Hey guys, does it work? Did I mess up? Oh, that sucks. Thank you. That was e to the x minus 1. Thank you for doing that, which gave me 1, didn't it? Aw. But yay. Because if you get really close to 1, and that's e to the 1 minus 1, that's e to the 0, which is in fact 1. So guys, what do you know is that j is stuck between 1 and 1. So what are you sure of? I'm thinking it's 1. I think it looks pretty good. The limit as x approaches 1 of j of x is 1. Now there's a really, really cool thing that we're going to look at. This is amazing. This is really, really cool. So just kind of bear with. We're going to study this soon. That's a hard one to decipher. Because what does a sine wave do? It goes like this, right? And as I get really, really, really close to 0, I start dividing by larger and larger things. But, you know, if you do that, don't you get 0 over 0? That's a really, really awkward thing to graph. And the question is, what does it get close to? There's really not a good way. So what do you guys think it would get close to? You took the sine of x and you divided it by x. As x gets really close to 0. Any guesses?
Well, what's the sine of 0?
The sine of 0 is 0.
Then it's a removable discontinuity wherever it is.
Well, it kind of sounds like a removable discontinuity, but what is it get? Is it getting close to something? See, sometimes it does and sometimes it doesn't. We're going to have to talk. So anyway, here we go. We're going to go to this next one. Now, we talked about 0 over 0. This is really super important that you know this. 0 divided by 0. We talked about how you always want to just plug things in, right? It's really good just to plug it in and hope to see what happens. But when you plug in directly to some problems, you get identically 0 over 0, which we talked about last year as a removable, right? But in here, I'm going to tighten that up a little bit because it's not always a removable. What it's called is an indeterminate form. Now, right up above, you're going to see some of these things. There are some times that 0 divided by 0 will be 6. There will be other times that 0 divided by 0 will be -8. Other times 0 divided by 0 will be no answer. You can't do that. Why do we call it indeterminate? Because you can't tell it from that alone. It means further investigation is going to be required. And this is one of those cases. So notice it says factor and divide out. So that's what we're going to do. We're going to start by rewriting this as x plus 2x minus 2 on top. And now here's the deal. When you say limit, are you allowed to plug in the number 2 technically?
No.
No. What does it say? What does a limit say? Technically, it says get really super close, but what? Don't touch it. So why can I cancel those out? Is because I promise I'm not going to touch it, right? So as long as I don't touch it, are these two things going to be identical and have the same weird little decimal divided by the same little decimal down here, which would therefore cancel out?
Yes.
But what happens if I do touch it?
4.
Then it becomes undefined. Then something bad happens. We talked about last year, the guy would say, go to hell, right? It was that really super bad thing. But see, what happens if this gets really super close to 0? What happens if I get really close to the number 2?
It gets really close to the number 4.
Really close to 4. So this answer is 4. So when we spoke last year about the removable discontinuity, what I want you guys to understand is the point that was plucked out of that graph was the point 2, 4. So this graph would literally come along like this. It had a slope of x plus 2. It's going to be coming along like this. At 2, 4, there's a spot that's missing. It would look just like that. How big is that flaw? Infinitely small, which is why that limit still exists. So do I get 0 over 0 in this one? In letter B. If I plug in 1 cubed minus 1, that's 0. Yep, it is. So again, we're going to try to factor it out. So I don't know if you guys remember how to factor a difference of cubes. I'll give you the first part. There's an x squared there. What's x times -1? So we write plus x. And then plus 1. That's kind of how it plays out. Square it, pop them together, and change the sign goes here. So guys, What does this get really, really close to? If you get really close to 1, in this case, 0 divided by 0 gets very, very close to what value?
3.
Oh, that's weird, isn't it? In other words, the limit is 3, that's a fact, but that means the coordinate of that removable discontinuity is 1, 3. Let's try that. Take out your calculators. I wish I had a slightly more fancy one. Mr. Corpy, he has this really nice electronic one that has pretty print on it and everything. It's like, it's really nice, but I'm going a little old school. But let's see. So my question said to get really close to what? 1. So would that be close enough? What do you guys think? I said the answer was 3. Does that seem plausible? So
Yeah.
what else should I try? Because remember, the definition of limit says go to the high side and the low side. So I did 0.99. What should I try now?
1.00001.
Sure, we can put as many zeros as we want. I tried something, was it in here yesterday that I blew over the top of the memory? Yep. Yeah, that was nice. Good times. Anyway, but does that kind of quickly convince you that we did that problem correctly? So in the first problem, 0 divided by 0 was 4. This time 0 divided by 0 was 3. Why don't you guys figure this one out? Now there is a hint. There's a hint. You see how it's asking for x going to -1. That's a hint that the top and the bottom are going to have what factor? See? X goes to 1, so it was x minus 1. X goes to 2, it was x minus 2. So if you're going to -1, what's the bottom going to have a factor of? I'm pretty sure the top and bottom are both going to have a factor of x plus 1. So let's see if you can remember how to do that. You might consider long division. You might also consider synthetic division since we're dividing by something simple. See if you can remember how to do that for a moment. I did a little synthetic division off the side. I took x to the 4th, 1x cubed, 3x, and 4. I put them over here. Ooh, that's ugly, isn't it? What does the bottom get close to? As you get really close to -1, what does the bottom get really close to? So the bottom is getting really super close to -5. I agree with you there. What does the top get close to? Well, let's just do it. Let's see, that's going to get close to -1. What's this going to get close to? -2. This is going to get close to -1, and that's getting, well, -4 is getting pretty close to -4, I think. So when I put all that stuff together, what's it getting close to? I think I got 8/5. By the way, 8/5, that is, as a decimal, that's 1.6. What would happen if you started doing the y1 of, and you started picking numbers really close? Do you think we'd get numbers really, really close to 1.6? In fact, we would. So I'm going to go ahead and leave that. Now, I need to get into these because this is actually where all of a sudden things get a little bit tougher. Sometimes you have these problems that have roots, and we actually did this last year a couple of times. We did not do it a lot, but we did it some. See, when you plug in 0, what does the top do? It goes to 0, it goes to root 1 minus 1, which is 0, isn't it? And the bottom goes to 0. This is one of those problems. Can I factor it? No. So here comes the big, nasty step. Whenever you deal with problems that are of this kind of nature, you have no choice but to kind of hit it with a pretty big, big bat. And that is rationalizing that denominator or the conjugation. So in this case, I'm going to take this guy right here, and I'm going to hit the top and bottom by something. You guys remember what the whole rationalizing thing is, that whole conjugate concept? You take big ugly up top, and what do we do to it? We switch the sign in the middle. So we're going to hit the top with this guy, and we're going to hit the bottom with the same thing. So have I done anything to the problem if I hit the top and bottom by that? Now, here's the cool thing. Why did we do that? Did it have anything to do with the bottom of this fraction? It had something to do with trying to make the top better. So what I'm going to tell you is when you do this, leave the bottom in factored form because it was collateral damage. It had nothing to do with the reason I did what I did, okay? What happens on top then when you actually distribute this? What happens when you do your, I know some people hate the word FOIL, but when you do that full distribution, you get root x plus 1 times root x plus 1, what do you get? You get x plus 1. And we don't need to do the outer or the inner because those are going to cancel. That's why we did the conjugate. So I get x plus 1, and then I get a minus 1, don't I? What does that leave us with on top and bottom? X over x. What can I do with that x over x? Can I cancel it just like I did here? Why am I allowed to cancel it? It's really, really important because what am I telling someone? That I'm not going to quite touch that 0. I'm going to get super close to it, but I'm not going to touch it. So I'm going to be able to take that limit. I'm going to have that x on top and that x in the bottom. I am going to go ahead and cancel that because I promise that I won't literally touch it. So what happens as I get really super, super close to the number 0, everybody? That's 1. What's that? 1. So grand total of 2. So what does that make the limit of this problem? What's on top? Wait, what's on top? X divided by
1.
should be
1 is on top. It's 1/2.
It should just be 1 on top. It should just be 1/2. Now, does that feel awkward to you? It honestly should. It should feel awkward. So like if you were taking a test and I asked this question, would it be valid to do y1 of 0.01 and make sure you got something that was very close to 1/2? Yeah, go check that answer. I want you guys to try that one. Whose collateral damage this time? Is it the top or the bottom that is the one that is collateral damage? The top becomes collateral damage because I'm trying to fix the bottom. So see if you can hang with that one. And let's see what kind of answer you get this time. You guys kind of see a quick confirmation that you did right? What happens in the bottom if you did it right? Didn't you get x minus 3? Why is that a fantastic thing for you? Because that one thing that produced that 0 on the top and the bottom, what just happened to it, everybody? It went away. That tells you, I love that when I was in calculus, because I could see, oh, I'm doing good. I can tell I've done something well with this problem if that happens. So what happens is I get really close to 3. Looks like root 5 plus another root 5 over here. So what's the limit getting infinitely close to is? What's root 5 plus root 5? 2 roots of 5. It's getting infinitely close to 2 roots of 5. So sometimes you can just plug things in. We saw that. Sometimes you can factor and do that. Sometimes you have to be a little bit more obnoxious. I don't think we got to this last year. You see how this is a problem too? Where instead of dealing with radicals, every year at the very end of math analysis, I take people through these very same problems. But last year was our outlier, right? Since we didn't see each other for the last month and a half of school, we didn't get here. So any guesses what I might want to do to clean this? I hate writing problems this way. Any guesses what I would do to clean this particular question up? I would multiply by, I mean, honestly, what's bothering you about, yes? Yes, you may. Okay. Does the fraction in a fraction, does it bother you a little bit? So could I multiply the top by 2 plus x and 2, and the bottom by 2 plus x? Would that change what happens there at all? As long as I hit the numerator and denominator by that lowest common multiple. Well, what happens if we have done well? Now, by the way, I didn't show the check, but by the way, if you tried to plug it in, you would still get 0 over 0. All of this lesson is about getting 0 over 0. But check out what happens on the bottom. Now, that was what I call collateral damage, so I'm not going to do anything to it. What do you think I'm going to hope goes away in my problem? X itself. Why do I want x itself to go away? Because as x went to 0, didn't that put a 0 on the bottom? So if I can make that x go away, life is going to be better. So let's see what happens. What happens when this gets hit with this piece right here? 2 plus x times 2 hits this. What's going to be left? Just the 2. And then when these hit, I still have the negative there, but the 2's would cancel and I get 2 plus x. Well, gee, what just happened? On top, be careful about this. The 2's are gone, right? What's the only thing left in the numerator? Negative x. Oh, boogers. There's a negative in this problem. It's negative x over all of this stuff. So could I now, as long as I promise, and I'm nice, and I don't really truly plug in 0, could I cancel those out? And what's going to happen is I get infinitely close to 0. What's the top? It's negative 1. And what's the bottom? Really close to? 4. Which is cool. It actually does work. Okay, your turn. What are you going to multiply by? 6 and x minus 6. You're going to leave that numerator in ugly form, in factored form, but you're going to multiply that bottom out and see what happens. My goal is to get through one more piece of this, and then we are going to, so 9 and 10, and then that's where we're going to be able to end today. Yeah, the sledgehammer's coming. That's the next. I love the sledgehammer. By the way, I didn't actually calculate it. I just used my calculator. I wanted you to calculate it, but what do you guys think the answer should be? Isn't that kind of nice to have the answer key? Kind of like before you start the problem, you could know what answer you're looking for. I'm pretty convinced negative 36 is the right answer. Do you guys need to go over that one, or are you okay? Are you guys okay? Thumbs up? No? Not thumbs down. Okay, thumbs down. Cool, let's look. So I'm going to hit the top with a 6. I'm going to hit the top with an x minus 6. I'm going to do the same thing with the bottom. Now, in the numerator, it is still a limit. By the way, I hated this when I was in your shoes. Keeping writing those limits. Are they important? They are. Ugh. It's like a square root or something. Boogers, I hated always writing those limits. So I still to this day sometimes forget, and I have to go back and add my limits to those steps. But I still have an x on top. I still have a 6 on top. I still have an x minus 6 on top. What happens in the bottom? When this hits this, what's left? Careful. The 6's would cancel. This times this is going to leave an x minus 6. When these hit, it's going to leave the 6. Now, ultimately, what that means is you now still have the x, the 6, the x minus 6 on top, and what's on the bottom? Just x. So those are going to cancel as long as I don't physically touch it. So as I get really close to 0, that is still a 6. And what is that? A negative 6. So 6 times negative 6 looks like negative 36. That looks like we actually got what we wanted. Now, all right, here we go. Yes? Well, okay. Let's talk about that. Guys, when you cancel, so, okay, this is kind of a little bit of it's kind of a nuanced basic math question, but it's not as simple as it sounds. Why can you cancel a 5 and a negative 5 when you add? Because technically they're additive inverses, and together they add up to 0, don't they? So what is division the inverse of? Division is the inverse of multiplication in the same way that addition is the inverse of subtraction. The reason you can cancel this x with this x is, see how this x is being multiplied? Therefore, that x can be divided. If I went right here, see this x minus 6? Why can I not cancel them is because they're not technically all being multiplied, because what's also part of the story? That addition. See, you can only cancel things if they are a perfect inverse. That's why factoring is such a big deal when we do problems in math, like back in here. Let me see if I could find it. Where was it? Right here. Why could I cancel these x minus 2's out? Because I wrote it as a multiplication story, and since it was a multiplication story, I can execute the inverse operation and cancel them out. But I could not cancel out the x squared and the x yet, right? I had to wait until I had first factored it. That's a nuance, but it's pretty important. Okay, the sledgehammer, does that sound cool? Okay. Okay, everybody watch this because this is not on there. I'm going to show you a picture. It's pretty important. So let's imagine, if you guys will, that this is some story, some function. I'm going to call it g of x, okay? What is the name of any point is x comma g of x, right? Would that name literally every point on this thing? Now watch how this works. What if I moved to the right h and I wanted to find that location right there? What would it be? It would be x plus h, because I moved to the right h units, right? And the y component would be g of x plus h. Now, if I played connect the dots with these two values, could I find the slope of that line? So what would happen? So if I did g of x plus h minus g of x all over, that's the rise, right? This one minus this one over, what's the run? It would be x plus h minus x, which is just h. What am I saying to do? Let's find the slope of that line, but let's bring those 2 points. What would this do? Bring those points where? Really, 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 really close together. Do you follow me? So that's instead of finding what this would be called, which is an average rate of change, what would this be? Instead of an average rate of change, this one would be an instantaneous rate of change. I want to find out the slope, not over a region. I want to find a slope right now. Now, would this give me 0 over 0? Look at it. It definitely will. So what we need to do is take a look at that with that lens of the sledgehammer. So is this right now 0 over 0? Look at it. Each of these problems is the story I just made for you. Well, the sledgehammer is as bad as it sounds. It's like putting your head down and just running into it and knocking things over. So here's what we got. It's the limit as h goes to 0. Oh my gosh, if you screw this up, I'm going to be angry. If you take x plus h and you multiply it by x plus h, that's x plus h squared. What is x plus h? Times x plus h. That's x squared. Plus 2xh plus h squared. Now, I know that's really hard for people to do. That people forget that. But literally, x plus h times x plus h. What's first? X squared. What's the outer? xh. What's the inner? Another xh. That made 2 xh's, isn't it? And then what's last? H squared. So I got all of this, but then it says take x squared away, and in the bottom what we have is h. Now, so far, do you notice anything that is convenient that happened for us? Oh, the x squareds cancel. Now, because all of those x's canceled, what is left that the top has in common? Oh, so that means what I can do is I could factor an h out of the top and leave 2x plus h all over h. Hey, wasn't that what we wanted? Didn't we want that thing that put 0 in the bottom to go away? Is that going to go away now? Ooh, what's left as, careful, what happens as h goes to 0? You know what you guys just found out? That the slope of the parabola x squared is 2x. So if I literally took a look at this parabola right here and I said, hey, what's the parabola's slope at x equals 3? You know what the slope is? It's 6. What's the slope over here at -1? It would be -2. How many slopes did we just find?
All of them.
All of them. Hey, you know what? Where is the slope 0?
0.
Could I decide, hey, where is the slope going to be 4?
Mm-hmm.
It would be at x equals 2, right? And you could do that. So here's what I want you guys to do. This is finding the slope of the line. This one is a little different. This one started with x squared minus 2x plus 1, and we're going to try to find the slope of that one. So notice all of this, all of that is f of x plus h. This is f of x all over h. Can you guys blow that one out? Blow that one out. Clean up your room a little bit and see if you can make that one work. We're really close to being done for the day. Wanted to get to Senor Salta and the sledgehammer. Those are the two that I wanted to talk about. if we'll even get to see more stuff. But we'll do this one a week good. Oh, man. It's huge. Terrible. These suck, by the way. If you make a careless mistake, you're screwed. Does anything cancel everybody?
All of the independent x's cancel.
X squared's dead. What else goes away?
2 x's and the 1s.
The 2 x's go away. The 1s go away. Now, by the way, that's confirmation. What does everything left on top have in it?
H.
That is fantastic. Everything on top has an H. So if it has an H, I can factor it out. Let's be careful. What's left if I factor out that H? 2x. There's an H there. And
-2.
a -2 there. All over H. Those cancel. So as H gets infinitely close to 0,
2x minus
so
2.
the slope of this thing is 2x minus 2. So if I asked you, check this out, this is so cool. If you wanted to know the vertex of this problem before, you had to do something weird. But check it out. When is this slope 0? Can you see it? When would this thing hit 0?
1.
At 1. That tells you the vertex of this thing has to be at 1. Hey, what's the slope of this guy at 5? It's 8. We just found literally all of the slopes. Isn't that kind of cool? You can go through that process, and we can do it with anything. And how do you know if you did all of this work right in sledgehammer method? What goes away every time?
The H.
That denominator, that H. How do you know if you did these problems right? Is the missing little piece here or here, it also cancels out. It's one of those zeros is going to go away, which is going to break the 0 over 0 logjam. You guys follow? That's kind of where I wanted to get to today. So today's homework, you guys are going to work on algebraic limits. And as you go through those, what I wanted to be a little bit clear on is that eventually you're going to get into some problems that start having some signs in it. This is a little bit unfortunate. You don't deal with anything that has the trig in it, and don't deal with anything that yet has the absolute value in it, okay? Those two things, they're interspersed throughout because I wanted to get to the whole thing, but I kind of knew it was just too long, and it's okay. So I'm going to hand you this, but you're going to, for right now, skip anything that has the trig in it and skip anything in it that has absolute values because we haven't handled those two stories. So I'm going to give this to you as homework. You're going to be able to do probably 75% of it. That last 25 we'll pick up on Monday of next week because I'm really sorry you guys won't have math for the next couple of days. Super sorry. No, and for some people that is a bummer because you're like, oh, that means I have English. Oh, shoot. So anyway, everybody has their own sensibilities. Do you guys have that where you like have sciences on one day and, or you guys all come in one day? See, some of you guys got really nice schedules that way.
I don't have the rest of the week.
You don't even have the rest of the week. Well, that's actually really, really nice. You just get caught up on things. So
I have Mondays, Tuesdays, and occasional